Good morning, everybody, and welcome to the second day of the ERCDL 2021 conference. We are very happy to have you here, and today we will start with a session on information and knowledge. The first paper will be presented by Ornella Irrera, and the title is Background Linking, Joining Entity Linking with Learning to Rank Models. So, Ornella, please go on. Perfect. We can see your screen.
Thank you. Good morning, everybody. Today, I present the work I did with Professor Gianmaria Silvello. We focused on learning to rank. In particular, our goal was to study the impact of a set of entity-based features. We organized our discussion as follows. After a short introduction, we described the proposed solution and our experimental setup. Then we describe the results obtained, and we conclude with some considerations and the future works. We developed our work in the context of the background linking task belonging to Track News Track 2018. Its primary goal is to tackle the possible lack of context and background information users may have reading online news. In particular, the reference collection for this track was the Washington Post, which counts about 600,000 documents published in the Washington Post from 2012 to 2017. 50 topics were provided and 5 relevance grades were provided for this task. We relied on Lambda-Mart learning to rank algorithm because it is one of the best performing algorithm in learning to rank algorithm in the literature. And it has a list-wise approach, and it is based on multiple additive regression trees. In particular, we based our learning process on features extracted from 2 different representations of the same document, the original textual representation and a graph of entities. In particular, we think that the entities together with the relationships can give a valuable contribution in relevance identification. In the last 5 years, there are several solutions which involve entities or the combination of words and entities. But the most interesting to our case is the one proposed in 2017, where the combination of words and entities allowed to obtain excellent results. Our starting point is the creation of a baseline. In particular, we applied the BM25 model to our corpus, and according to the guidelines, we retrieved 100 documents per topic. This baseline is extremely important for 2 reasons. The first one is that we use the documents in this baseline as test set during the learning to rank task. While the second one is that the results of the baseline are a useful reference point to compare our results with. We firstly created for each document the related graph of entities. First of all, we performed entity linking in order to annotate the textual document with the Wikipedia entities. And we used this bag of entities to create an undirected weighted graph, whose vertices are the entities retrieved, and the edges are inserted on the base of the semantic relatedness existing between pairs of entities. At the end of this phase, we obtain a graph which is usually subdivided into connected components. In particular, the largest connected component is characterized by community structure, where there are the most meaningful and important entities for context identification, while the other minor connected components usually contains entities which derived by errors in our notation. This is why we want to perform pruning in order to discard all the out of context entities. and we kept only the largest connected component, and we ran the Girvan-Newman algorithm for community detection in order to obtain the largest community where it is more probable to find the most meaningful entities. And let's see a practical example. This is a portion of an article about tropical storms. We firstly find the terms which have a corresponding Wikipedia entity, and these are the entities associated. This represent the entire textual content. And now we create the graph. Well, it is now possible to perform pruning. We firstly discard the minor connected component, which contains out-of-context entities. And then we run Girvan-Newman algorithm in order to remove Earth and explosion, which are too general for context identification. And we obtained our final graph. We extracted two sets of features to include in a document's vector representation. The first set is the textual-based set, which include features dependent of the query document, and these are the M25 score or the time frequency, but they can also be independent, and we can find the document length. The other set is the graph-based set, and also in this case we have query graph independent features, and in this case we have topological properties of the document's graph, such as the node connectivity. And we have the largest subset, which counts 43 features, that is the query graph-based set. And we show an example of this kind of features. We have two graphs, the query one and the document one, and we find running the betweenness centrality measure the most influential node in both the graphs. And we replace the most central entity of the query graph with the one of the document graph. And we compute the new semantic relatedness between the document's central node with its new neighborhood. The final feature is the average of the new semantic relatedness computed. And the higher this feature is, the more probable is that the document contain valuable context information about the query document. Then we run learning to rank, in particular, starting from a training set and an effective hyperparameter combination, we can automatically construct a ranking model. This is used by the ranking system to re-rank the documents belonging to a test set. In particular, we obtain as output a final run which contains the documents of the test set, but with a different ranking. The final phase of our implementation is the fusion. In particular, we considered at most 10 runs, the most belonging to the most effective models, and we combine them with the CombSum method. This phase has two goals. The first one is to try to improve the retrieval results, and the second one is to study whether an increase in the number of runs fused can be corresponded by an effectiveness improvement. Let's see some technical details. We annotated each textual document with the TagMe RESTful API, and we annotated at most 30 entities for each document. This settings approach derives by a study conducted on 30 textual documents of the corpus. In particular, this leads to graphs with at most 30 entities. And we set a threshold on the edge insertion. This threshold, equal to 0.4, is extremely important because it allows us to have a graph subdivided into connected components. And it allows us to have the most meaningful entities in a unique connected component. We trained Lambda Mart with a training set composed of 21,000 vectors, and we used two disjointed sets of topics for training. One set was the one provided for the Common Core track of 2017, whose reference collection is the New York Times annotated corpus, while the other set is the one provided for the News Track 2019. Whose reference collection is the Washington Post corpus. Even if training set and the test set share the same collection, that is the Washington Post corpus, the sets of topic we used were all disjointed. Even if introducing the New York Times collection allowed us to enlarge the training set, and so we can increase the accuracy of the learning process, it made our system suffer all the consequences brought by the transfer learning. In particular, the most influential one is the lack of consistency between relevance grades. In fact, we had to map the 5 relevance grades belonging to the Washington Post corpus to the 3 provided for the New York Times annotated corpus. Then we manually tuned the hyperparameters, and we selected the 70 models the best performing in terms of NDCG at cutoff 5 in the validation set. We firstly performed a quantitative analysis, which allowed us to study how our system performs on average. We reported the performances of the best models run, that is the best run, and then the best performing fusion runs, which correspond to the fusion of 2, 3, 5, 7, and 10 runs. And then we report also the performances of the baseline. If we consider an analysis of only one document per topics ranking, we can see that our system always outperforms the baseline. And in particular, the best performing run is the fusion of 5 runs. But if we study the performances of the topics rankings at different cutoffs, we can see that after 5 topics, 5 documents in ranking, our performances decrease as the number of documents considered increase. And this is partially caused by the transfer learning. If we can make a first consideration, in particular, the increase of the number of runs fused is not corresponded by an increase in the performances. In fact, the fusion of 10 runs is the least effective run. If we consider our primary measure of effectiveness, that is NDCG at 5 documents in ranking, we can see that the best models run approximates the results obtained by the baseline. And we can see why performing a qualitative analysis, which involves the specific topics, in our case, of the best models run. In particular, we represented an histogram where we represented the topics belonging to the best run, and for each topic we put into relation its results in terms of our best models performances and those of the baseline. In particular, above the abscissa, we can find all the topics where our system outperforms the baseline, and vice versa holds for topics below the abscissa. We can see that there is the same number of topics where our system prevails over the BM25 models, and the number of topics where BM25 models outperforms our baseline. And this allows us to understand that these two systems fits disjointed sets of topics. And there is never a system that always prevails over the other one. This analysis allowed us to understand what the advantages and the disadvantages are of our system. Starting from the advantages, we can see that the graphs played a crucial role for those topics in which our system prevailed. In particular, this topic showed in their rankings documents whose relevance was detected both from a point of view of graphs and from the point of view of textual features. And moreover, our system always manages to put in the first half of the ranking all the relevant documents. And it is particular a case of a topic whose relevant documents were only 6, and they were placed in the first 12 position of the ranking. For what concerns disadvantages instead, we can see that transfer learning has a strong impact in our implementation. In fact, it prevented some topic to reach their highest results. And it prevented also our system to perform in a good way after 5 documents in ranking. And moreover, we noticed that there are some errors during the learning process. In particular, sometimes the value of only one feature influenced the entire topic's ranking, and the remaining part of the vector was not taken into consideration. Finally, we could understand what the cases where it was convenient to use the BM25 model instead of our system. In particular, graph strongly depends on the textual content of a document. And if a document is relevant, but it contains a really short textual content, its graph could not represent its relevance in the best way. Moreover, we notice a case of a topic whose documents have all graphs similar to the query one, even if the documents were not relevant. In this case, all the bag of entities were similar, so the graphs recognized the general topic the documents were about, but the final information these articles want to give to the user was not detected in the graphs. And in these last 2 cases, it is always better to choose the BM25 model instead of our system. I conclude with some further researches that can be carried out to improve our current system. The first one is the performance of an automatic tuning, and the other one is performing an ablation study discarding the textual-based features, and in order to understand what the real impact of graphs is. And I conclude. Thank you.
Thank you very much, Ornella. Thank you also for being on time. Is there any question for Ornella? Sorry, I'm not sure that I see one. Okay, no, I don't see any hand that is raised. So I have a question, and in the meantime, if somebody else wants to have a question, it just has to raise the hand, and I will give him the word. So Ornella, I was wondering, what is the meaning of the relevance in the graph? I mean, the weight that indicates the relevance. Is it computed on the basis of the specific document or of the relationship that exists between these entities in a bunch of documents? You see what?
The relevance of a graph, of a document in graph can be detected both from the point of view of the bag of entities, but the most important thing is the relationships which exist between entities. So it is a combination of the entities which represent the document, but also the relationships. Because
yes, my question was about the relationship. So the weight of the relationships. I was wondering, how do you compute the weight, you see, of the relationships? Yeah.
We computed it with the definition of semantic relatedness provided by TAGME, and it identifies the semantic relatedness that exists between 2 entities, and it identifies the similarity. Was this the question?
Yes, but this similarity, is it computed on the basis of a big set of documents or on the basis of the single document that you are considering?
on the basis of the single document we are considering, because we firstly extract the entities and then we compute the similarity between entities, between pairs of entities.
Okay, I see.
Yeah, but Antonella, how do you calculate the similarity? I think this is the Antonella's question.
Well, yes.
What do you use to calculate the semantic similarity between the entities? Or TAGME, what does TAGME use?
TAGME uses its the definition we can find in the literature of semantic relatedness, which is based on the incoming link on Wikipedia pages. So it is computed between pairs of entities.
I see. So a relationship that is of type instance of is considered exactly as another relationship between, let's say, brothers, let's say some relationship between entities, single entities that you could have in a graph on instances. Yes. Mm-hmm. Okay, I see. Okay, because this makes a little bit difference now, because I mean, if you I saw that you skipped HERF because it was too general, storm HERF.
Yes.
But probably there was a relationship of type instance of, and this kind of relationship is very different from the relationship that says he lives in.
Yes, that's true. But we were interested in the entities that could contextualize the original document at best. So we were more interested in the semantic relatedness, and we performed the discarding of the entities on the base of this measure.
Okay, thank you. Is there some other, are there some other questions? No. Okay. You can